Today we're going to start looking at the idea of a rational equation. And before we do that, we need to flash back to a couple of ideas. The first is the concept in mathematics of equality versus equivalence. Now, equivalence is when you have equality of value, but not appearance. So equivalence is when I say this. We say 2/3 equals 4/6, but really we're saying that they are equivalent. They have the same value, but they look different. That's equivalence. If I say something like this, 2/3 equals x thirds. When I state equality, this is very strong because in math, equality means equal in every possible way. So when I say 2/3 equals x/3, that means that the left and the right are identical. They are equal in every possible way. So that means I can break it down. If this denominator is the same on both sides, then the only way for true equality to happen is if these two numerators are the same. And that's why it's almost like we can say that the two denominators don't exist and that 2 has to equal x. It's the only way for equality to be achieved. If this had said x plus 1 instead of x, I could now say this is x plus 1. Subtracting 1 from both sides would lead us to x has to have a value of 1 to achieve pure equality. Same here. If I go back to our equivalence of 2/3 is equivalent to 4/6, well, if I reduce 4/6 by dividing top and bottom by 2, I can take the equivalent fraction of 4/6 and change it to that pure equality of 2/3 equals 2/3. Now, why is this important? Well, we're going to use that fact in solving a rational equation. And remember, equality happens when there is an equal sign. And when we have an equal sign, it opens up doors we don't have when we are dealing with expressions. So let's do a flashback. Here is an equation that just has fractions in it. Now, could we subtract 7/5 from both sides and then double or divide by half? Sure. Or we could get more creative. Let's get a common denominator for every single part of this problem. Between 2, 5, and 6, the common denominator here is 30. So I'm going to upgrade every part of this problem to have a common denominator of 30. So I'm going to rewrite every single term with a denominator of 30. I am now going to upgrade each one to its equivalent term. So remember, equivalent means I'm not going to change the value of each term. I'm just going to change its appearance. So this is still going to be a 1/2 x. It's just going to be its 30th version. 15 of them, in fact. Here, to turn 5 to 30 is times 6. So that's going to be 42 30ths. Here is times 5. So that's 25 30ths. Now that they're out of 30, everybody, I can add these two fractions by adding their numerators. And here we are once again with one of those equality statements. I have something over 30 equals something over 30. This is a true equality. I have 30 and 30. If the denominators are both equal, the numerators must both be equal to maintain that true equality. So it's almost like those denominators don't matter anymore. And so now I can solve. I mean, I get a pretty terrible little fraction, but it's doable. And you'll notice we did it without a calculator. That's the even cooler part. This was back in the days of Algebra 1, when our denominators were all numbers. What happens now when our denominators are not numbers? Let's take a look. We are solving. And remember that when we solve, especially if there's the potential of any kind of solution that could cause problems, we need to be careful what we do. So let's try this. I notice I have a common denominator across the board. Let's go ahead and add. This both common denominator, I get 16 over x equals x squared over x. Both of these denominators say x. If both of these denominators are the exact same thing, then to maintain the equality, the two numerators must be equal. Now, if I solve, I get 4 or negative 4 as my two solutions. Now I need to go back and check to make sure they work. I'm going to, of course, plug them in. 5 over 4 is 5/4. That's 11/4. That would give me 16/4. That's 4. And then 16 divided by 4 is 4. So we're good. If I put in negative 4, that's negative 5/4. Negative 11/4. That's negative 16/4, which is negative 4. And then 16 over negative 4 is also negative 4. They both check out. And so my solutions are all good. Let's take a look then at what would happen if we broadened this out into something even more interesting. Now we've got polynomial denominators. This is where things become a little bit trickier. So here we're going to need to follow some steps. Let's get those steps down. Step 1. We're going to need an LCD. So we need to factor all of our denominators. This one's good. This is a dots problem. Now, we're going to have to find our LCD. So by doing our tricks where we think about what's allowed and what's not allowed and what we can do. So I see I have an x minus 2 here. I also see it there. And then I see we have an x plus 2 here. So if I look at my LCD, it's x minus 2, x plus 2. At this point, we're going to have to take a little bit of a pause. Because this is an equation, and because we're going to get some answers later on, we need to stop. And we are going to find the forbidden x's. In other words, we know that with x's in a denominator, there are values that x are not allowed to be because we are not allowed to divide by 0. So what values of x would make our LCD equal 0? That's the question. So what makes the LCD equal 0? In this case, 2 or negative 2 would make the LCD 0. So we are going to say that right now, no matter what happens in this problem, no matter how it turns out, x is not allowed to be 2 or negative 2. We're just going to say that right now, no matter what happens, this is what x is not allowed to be. All right. Step 3. We're going to scale the fractions to the LCD. So I'm going to take my original fractions. And I'm going to see what they need in order to have the LCD. So now, the first fraction only had an x minus 2. It looks like it needs an x plus 2. So I'm going to go ahead and give that top and bottom. The other fraction already had the LCD. So I don't need to do anything whatsoever. Step 4. I'm going to simplify the left and right of the equal sign in order to get this picture. Something over the LCD equals something over the LCD. So I'm going to do whatever math is necessary. So here I have negative 2x minus 4. And I'm just going to go ahead and write LCD at this point. And on this side, I have x minus 4. So there we go. Okay. Now, I've got our equality statement. Something over that equals something over the exact same thing. I have my pure equality. To make this true, I know the two numerators have to be the same if the two denominators are the same. So that means that I'm solving the numerators. Basically, I'm going to dump my denominators. And a lot of times I'll just say for short, let's dump the denoms because I'm too lazy to write denominators. But then that a lot of times looks like demons instead of denoms. So in this case, I like to say, let's dump the demons. Let's just get rid of our denominators because fractions are evil. And we dump our denominators. We set our numerators equal, and now let's solve. So we subtract x from both sides. We add 4 to both sides. We divide by negative 3, and we get x equals 0. And now, step 6, we have to check any solutions that we get. So did we get a forbidden x? So did a solution that we got fall in the list of forbidden values? Nope. This x is not in our list of forbidden. And if I wanted to go back and check, if I put 0 in, I get negative 2 over negative 2. That's 1. And over here, I get negative 4 over negative 4. That's also 1. So this checks out. All is good. And there's our solution. That's the basic idea behind solving rational equations. Of course, they get more complicated from there, but that's how it works.